Okay, let's calculate these acid base units. So I've got some hydrogen ion, and here's my concentration. Can you tell me about what the pH is, just looking at this number without doing any calculation? Some below 5. Definitely below 5, but not below 4. It's somewhere in between 4 and 5, for sure. So we know that because if we didn't have this part right here, this 2.95, the pH would be exactly 5. But we've added a little bit more acid, so then that brings the pH down to 4 something or other. So an answer to that question would be, I don't know, 4 something or other, because that's what it's going to be. And so if you actually do the math, did somebody got a number for me? 4 something or other? 4.59. Great. Okay. So if my pH is 4.59, what's my pOH? And so then that makes my hydroxide ion concentration 10 to the negative 9.41. If you want to put it out in a whole number exponent, that's fine. It'd be something times 10 to the negative 10th. But those numbers are identical to each other. All right, so this time I've got a pH. And so if I've got a pH, I can get a pOH. And my pOH is going to be 11.64. Yeah. And so that makes my hydrogen ion concentration 10 to the negative 2.36. And my hydroxide ion concentration 10 to the negative 11.64. Okay. How about this one? What's the pH of a 0.2 molar solution of hydrochloric acid? So what do you have to recognize immediately? No. Strong. This one here and the next one here, these are both strong, one an acid and one a base. So what that means is if I've got 0.2 molar hydrochloric acid, I actually have 0.2 molar hydrogen ion concentration, right? And then this one down here, I'm going to have 0.2 molar hydroxide ion concentration. Okay. So if I take the negative log of 0.2, I'm going to get, what is it, 1? I don't know, like point something or other? 0.9? 0.7? Okay, so my pH is actually equal to 0.7. Is that very acidic? Yeah, it's really acidic. Okay. So I'm going to do the same thing down here. I'm going to take the negative log of 0.2 and I'm going to get, what's the difference here? Since I'm taking the negative log of the base's concentration, I'm going to get the pOH. So then my pH is whatever this number is, taken away from 14. So my pH for the second one is 13.3. So super basic. So those ones are pretty simple. You really just take the negative log of whatever the concentration of the acid or base is, and then it's either that's your number for your pH or you got to subtract from 14 if it's a base that we were talking about. The next two, what's different about them? Yeah, these are both weak. So we have to go through the process of squaring and square rooting the problem. So what I need to do initially is look up what nitrous acid's Ka is. So this is one of the last things we talked about when we left on Tuesday. Okay, so we've got nitrous acid here. And so there's its Ka, 0.62 times 10 to the minus fourth. So I've got a Ka 5.62 times 10 to the negative fourth. So this is, the reaction is HNO2, double-sided arrow, H plus nitrite. And so my Ka is hydrogen ion, nitrite, and nitrous acid. So first day we were talking about acids and bases. I said we'll use H plus a lot. And what's the problem with that? What's like fundamentally the problem with using H plus? It doesn't exist, right? But this is what everybody does. Everybody knows that it doesn't exist, but they write it because writing H3O plus takes too much time, evidently. So when you see that H plus, what should be going on in your head? Person's being lazy, it's really hydronium ion. That's what you should be thinking. It's not going to affect the actual calculation, so don't get in a huff over it. Okay, so what I know right now is the Ka is 5.62 times 10 to the minus fourth, and I know that the concentration of the nitrous acid is 0.2. What I don't know are my hydrogen ion concentration, which I need to calculate my pH, and my nitrite ion concentration, which I don't really need other than to calculate out the hydrogen ion. So what I do know about them is what? They're the same. So I can say that that's an X and that's an X, and then I can rearrange this entire equation and get X is equal to the square root of 0.2 times 5.64 times 10 to the minus fourth, and I get some number. All right, square root 0.2 times 5.64 e negative 4 close parentheses equals 0.011 or just 0.01. So what is this 0.01 a measure of? What is it telling you?
That's the concentration of H plus and nitrate.
Yeah, this is moles per liter of that thing and that thing. So there you go, I know my H plus ion concentration. So if I take the negative log of 0.01, I'm going to get, what, 2 is my answer? So the pH of this nitrous acid solution is 2. That's significantly different than the hydrochloric acid solution concentration, right? Less than 1 to 2. What's about the difference between those two things? One point 1.3 pH units, but what's about the difference? More than 10 times greater concentration of H pluses, because each pH unit is 10, so drop from 2 to 1, so that's 10 times more concentrated HCl at the same concentration, 10 times more H plus, and then it's even more than that because I'm at 0.7, not at 0.1. So equal concentrations of the two acids give a much higher concentration of hydrogen ion because the strong acid lets go of all the H pluses, where the weak acid holds on to a bunch of them in its weak acid form, and so it can't do anything to you if it's still stuck to its anion. Okay, so we're going to do basically the exact same thing that we did with the prior problem, but what's going to be a little bit different about it? The Ka isn't going to be a Ka, is it? What's it going to be? It's going to be a Kb. So we'll slide up here and we'll find hydrazine. So here's my hydrazine. So 1.26 times 10 to the negative sixth. Okay, so I'm going to put this in a completely generic format. So this is a weak base, right? What will a weak base generate? A hydroxide ion, right? Okay, so, does that make sense? So what's the X? No, it's my weak base, my hydrazine. Okay? And then what did that weak base do? No. It didn't give off anything. What did it do? No. What's different about the X from one side of the double arrow to the other? Now there's an H on it, so what did it do? It accepted a proton, right? That's Bronsted-Lowry's definition of a base. So if it gained a proton, where'd it get it from? There's no H's shown up here anywhere. Water molecule. So there'd be an H2O there, and this base, whatever the heck the base is grabbing an H off the water, because that's what bases do, leaving behind a hydroxide. So what we end up with is Kb is equal to you okay with that? You'll see this kind of thing written a lot, especially with the weak acids, where they don't even bother to put the acid or the base up there. You just know what the reaction is going to be. So in this case, it was hydrazine. So the hydrazine molecule is here. What makes this hydrazine molecule a base? The nitrogen's lone pair of electrons. Okay, so I've got, keep switching out of that. That's what actually happened in the problem, right? Or in the reaction. The hydrazine was messing around in the water, grabbed an H off of the water. It became positively charged, leaving behind the negatively charged hydroxide ion to float around. So what I know is this is 1.26 times 10 to the negative sixth. I know this is 0.2. I know that's X and X. So what I got is X is equal to the square root of 0.2 times 1.26 times 10 to the negative sixth. And let's get an X out of this. .0005. So I got a POH of 3.3. I took the negative log of the 0.0005. And so my pH is going to be what? 10.7. Okay. Potassium hydroxide and bromic acid. Okay, so HBRO3 plus KOH. When I take, so which one of these is the acid? not too tough with that. And the base, the other thing. What do you get when you mix an acid and a base together? You get a salt and water, right? So here's my salt over here. How do I know that this thing here is a salt? It's a metal and a non-metal, right? Okay. So this is going to be my conjugate base, and this is going to be my conjugate acid. So how do I know that the water is the conjugate acid? When we think about acids, what should pop into your head? Hydrogens. Who's got the hydrogens? The water. So the water could give away an H. That makes it an acid. Could the potassium bromate give away an H? Oh, no, H is to give away, right? So it couldn't possibly. But it could, the bromate could accept the H back and turn back into what it was before. And so that's our situation. The last thing we should put on here is aqueous, liquid, aqueous. How do I know that those three things I need to label as aqueous or aqueous? Not because there's hydrogen.
Because there's water.
The only way that these things could react would be if there's water, but that doesn't make them aqueous. Acids are aqueous, right? So that's why that one gets to be aqueous. Why is the potassium hydroxide aqueous? Because it's a group 1 metal, and so that's the same reason for the last one, also a group 1 metal. Which is stronger, hydrocyanic or acetic? And how do I know that? So let's go back over to this. So acetic acids, Ka is 1.74 times 10 to the negative fifth. And what was the other one, hydrocyanic? And that one is 6.17 times 10 to the negative 10th. So tell me what the Ka is letting a person know. The extent to which this acid is going to be disassociated. So the bigger the number, the more disassociated it's going to be, so the more H's you're going to get. So of these two, the acetic acid is about 10,000, is it 10? 5 zeros? 100,000 times more likely to give away its H's than the hydrocyanic is. So you could just write acetic.
So if you look at the pKa number,
It's the opposite then.
right, so the lower that you go on that list would be
The more
stronger
acidic.
acid.
Yep. And it's only because we get rid of the negative sign. When we take the negative log of something, that negative flops the sign around on us. So, so I've got 30 milliliters of this and 600 milliliters of water. What's my pH? Okay, so how do you calculate out a pH? What do you need to know? Negative log of what? What?
Concentration.
So concentration in moles per liter of hydrogen ion. So what I don't know right now is what its concentration is going to be when I drop it into this water. You okay with that? So what I need are moles and I need liters. There's two ways you can approach this problem. One, you can just use the dilution equation because that's what we're doing here, right? I'm taking this stuff that's 0.1 molar and I'm dropping it into some water, which is going to dilute the heck out of it. Or I could calculate out what the moles are and divide by the total number of liters. But I think the easiest thing to do is just say M1V1 is equal to M2V2. What don't I know this time? I don't know the concentration of what it's going to be when I throw everything together, right? So if I start off with 0.15 molar and I start off with 30 milliliters of it, I don't know what its concentration is going to be when the total ending volume is going to be what? 630. That's basically the tricky part of the question. The ending volume isn't 600. I put it into 600 milliliters, so then the ending volume is 630. So then my M2 is going to be 0.15 times 30 milliliters divided by 630 milliliters. So got I need to make it so it doesn't pop up automatically. 0.15 times 30 divided by 630. And so I got 0.007. And so negative log 0.007. I get pH is equal, oh, did I ask what the pH? Oh, yeah, I did, okay. 2.1, 2.2, 2.2. Okay. What was the pH before I threw the hydrochloric acid in?
0.82.
7. 600 milliliters of water, just water, so it's pH of 7. So I throw in 30 milliliters of this 0.15 molar and the pH drops to 2.2. That's like 10,000 times more acidic. Okay.